Okay. Go away. Hello. That's just about 8 o'clock. Um, I'm Sam. Hello. This is the Gen Chem 223 live stream. It's Friday night at 8 p.m. The sun has not quite yet set, which is nice. It must be almost summertime. So I am going to dive right in because we have a bunch of chemistry problems here that we want to go through, and we have 1 hour to do them. Although maybe I'll go a little extra long. I'm not necessarily beyond that. So here we go. I think that's all working. I, as usual, did a few practice rounds on these problems. So take a sneak peek at what's going on here. We are talking about solubility today, and solubility is all about stuff dissolving, specifically solid things dissolving into water and becoming aqueous things. Pretty much every time becoming ions. So let's just look at an example right off the bat here. This problem is talking about a saturated solution of lead sulfide. Now, sulfide, by the way, when it's an ion, it's S2. That's a sulfur atom with a couple extra lone pairs. I almost said alone pairs. Um, it's got a couple extra lone pairs and a formal charge of -2. And since it's a solid with lead and it's neutral as a solid with lead, it must be hanging out with lead in a +2 oxidation state. So by the way, we would call this lead 2 sulfide. And we would only capitalize lead if it were the beginning of the sentence, by the way. Chemicals are not proper nouns. Side note. Okay, so this is what we're talking about. And when the lead 2 sulfide, the solid lead 2 sulfide, dissolves, it creates some sort of equilibrium concentration of each of those ions. And it goes back and forth, as suggested by the back and forth arrows, but it reaches an equilibrium stasis. So it's reached some sort of stasis where it has as much of these ions as it can handle. If you were to add more of your starting solid material, the lead 2 sulfide, it would not dissolve anymore because we're at saturation point, saturated solutions. Here's the question now. What if we add potassium sulfide? So there's two potassiums there, one sulfide. We already talked about sulfides of -2 formal charge anion. We know that potassium, of course, is a +1 cation in aqueous solution. Just loves losing an electron. There's two of them. Oh, here, let me put this all in one line. We got some, well, there's very little backwards here. This is fully soluble, as we'll see in a sec, because I'm going to remind you of the solubility table. And we're going to get a ton of this. So if we add potassium sulfide, we're going to get a lot of this common ion, right? This common sulfide ion. So because of that, the concentration of sulfide will go up. And one way to conceptualize this question is through the lens of Le Chatelier. The Chatelier principle, which essentially says that if you have an equilibrium reaction or expression with a left side and a right side, if you do something to increase the right side, it's going to push the reaction to the left to make the left go up and the right go down so it can get back to its happy place. This is not a lesson about Le Chatelier, but it is one way to think about it, because by adding the common ion, we have increased something on the right side. So it would make sense that adding potassium sulfide, which increases sulfide ion concentration in the solution, would encourage the reversible aspect of the reaction to occur and generate more of our solid lead 2 sulfide precipitate. So it would decrease the lead ion concentrations by uh, driving the reaction to the left, increasing the right and driving left. So that would be the Le Chatelier's principal perspective on that. I do think we should pop over to what you can find. I annotated this a minute ago when I was testing Twitch. This is table 4.1. It's in the textbook, the open source textbook, and I'm sure all over the internet. And this is a guide for, if you don't just know, for deciding if compounds are going to dissolve in water or not. And one thing that this guide says is that if you have, zoom in, because I think it's probably pretty small for you. If you have a potassium cation, which we do, when we have potassium sulfide, we have a potassium cation, and that is soluble. And are there any exceptions to that? No. Exceptions, none. So potassium sulfide is fully soluble. Had we started with a sulfide, by the way, we would have noticed that sulfide is on the list of insoluble ionic compounds. So sulfide things we don't expect to dissolve, except exceptions, compounds with group 1 cations. Potassium is a group 1 cation, right? It's on the left column of the periodic table. That's group 1. So this table 4.1 tells us in two different ways that potassium sulfide is going to completely dissolve, whereas lead sulfide is going to barely dissolve. It's not soluble, so it'll dissolve only a tiny bit. Lead 2 sulfide, it's a sulfide containing compound, and it's not on the exception list. So from there, we're going to look up the KSP. Again, we already answered this question from Le Chatelier's principle perspective, but we can also go to, let me just note that this is Appendix J in the textbook, and I'm sure there are many other solubility product tables that tell us the KSP in standard conditions of many things. We're going to look at the lead. Oh, look, I circled it earlier. By the way, when I copied this, something weird happened. There shouldn't be two X's there, but we know that is 7 times 10 to the minus 29 is the KSP of lead sulfide. 7 times 10 to the minus 29. 7 times 10 to the minus 29 equals the KSP of lead sulfide. And look, the KSP of lead sulfide is the concentration of, oh, oops, my bad. I just started doing the second question. 7 times 10 to the minus 29. I missed when I scrolled over. Foreshadowing. KSP equals 7 times 10 to the minus 29 of lead sulfide. So I had started writing out the KSP expression for something else with lead in it. The KSP expression, like any K expression, is an equilibrium mass action. And we have the products, fundamentally, we have the products of reactants. And we only include aqueous species and gas, if there is any, but that's not pertinent to this. For KSP specifically, it truly is only aqueous species. And the other thing is the reactant is a solid. And solids, when it comes to K expressions, when it comes to mass action expressions, solids count as 1. So the KSP as a fundamental construct is products over 1. So it's just products. But of course, we need to unpack what products means a little bit better. And essentially, here's what it is. If you have, let's say, A, B, this is a solid of some sort, and it dissolves in some way. Actually, make those arrows a little bit more legitimate. It's probably much more like this. It doesn't like dissolving, right? But it dissolves in a reversible reaction, leading to And there's going to be some sort of charge here. And we will have to use that to balance some of these later. Oops, I should not have put parentheses. So the KSP as a fundamental construct will equal the concentration of whatever that A is to that stoichiometric coefficient, right? And then whatever the concentration of that B is to the power of its stoichiometric coefficient. In the case of lead sulfide, the stoichiometric coefficient is 1 in both cases. The formal charge is 2 plus for our aqueous lead cation that dissolved out of our solid lead sulfide. And the stoichiometric coefficient of the sulfide part, the aqueous sulfide, is also 1. So the KSP expression for lead sulfide is the concentration of lead to the 1 times the concentration of sulfide to the 1. And obviously I don't typically bother writing to the 1, but since it's the first problem of the video, I thought it'd be super thorough because this problem is worth spending a few extra minutes on because it sets us up for basically the next like 8 problems or something. So we obtained from a table, which was a compilation of experimental evidence, that the KSP of lead sulfide is 7 times 10 to the minus 29. And we have said that the theoretical construct that is lead, the KSP of lead sulfide, is the concentration of lead 2 times the concentration of sulfide. So that background information on KSP now finally brings us back to actually answering this question. How did the concentrations of these change? So we already answered it from Le Chatelier's perspective. Once again, if we're increasing what's on the right, then we expect the reaction to push left and increase what's on the left to compensate. So that's one way to look at it, but now we can look at it like this. When we dissolve our K2S, that increases the concentration of sulfide, and in doing so, the KSP doesn't change. The only way for the math to stay true here, which, we're operating with the assumption that math continues to function in these examples, the only way for the math to stay true is that the concentration of lead cation here has to go down. And how does the concentration of lead cation go down? It goes down by precipitating out as, wait, where do I have it? As this. The way for the concentration of lead cation to go down is for the reverse reaction to occur and for a lead and a sulfide to get together and become lead sulfide. Solid. So the potassium sulfide will increase the sulfide concentration when lead goes out. It'll take a sulfide with it. So there's a chance that if you added exactly the right amount of potassium sulfide, that maybe the concentration of potassium sulfide would go up and then down the same amount and it would cancel and lead would net go down. Chances are, since this dissolves so well, that you're going to add some excess amount. And so probably the sulfide will go up and lead will go down. Possibly the sulfide will net 0. Oops. But definitely the concentration of lead's going to go down because the not concentration, but the amount of solid lead sulfide will go up. So that is an intro to all that. Now let's write more KSPs. So as I just noted, KSPs are the products of a reactants with the stoichiometric coefficients. Oh, and KSP, the reactant is a solid, so it equals 1. So let's just bust these out really quick. Lead chloride, which is the one that I got confused about a minute or two ago. If that's a solid, Let's do these really quick. That is going to dissolve to some extent. Once again, I know it's going to be lead 2 plus this time in advance because I know that chloride is always a 1 minus. We had two of them, so lead must have been 2 plus for that to be a neutral salt. Okay. All right. The whole point was KSP. So the KSP of that is going to equal the concentration of our lead cation times the concentration of our chloride anion squared, right? We have that 2 chlorides, so we've squared it up there. So the green on purple, by the way, is an interesting aesthetic choice. And or not choice, but just something that randomly happened. Okay, the second one, silver sulfide. And we could, let's just look really quick, table 4.1. Until you have a good sense of these, which I only sort of do, it's always good to consult this table in case you forget what's going on. So check this out. Oh wait, are we doing silver? Sorry, I forgot the ion. Silver sulfide? Oh yeah, well I already remember from looking before. Sulfide is just not soluble. We looked before. The only exceptions were ammonia and group 1 cations such as potassium. So that's going to have poor solubility. I guess that's beside the point of this question. So let's just note that we're going with 2 silvers and a sulfide. Silver is an invariable cation. It's always +1. But if you didn't know that, but you knew that sulfide was, sorry, if you didn't know that, but you knew that you had 2 of them, and you knew that sulfide was 2 minus, then silver would have to be KSP here for silver sulfide. Silver 1 sulfide is what we would call this because the silver is a +1 charge. Going to be the concentration of your silver cation squared times the concentration of your sulfide. All right, let's do C. Strontium phosphate. Very fun. So phosphate, by the way, PO4 3 minus, it's a common polyatomic anion. So if we have 3 strontiums that are along with 2 phosphates, and that's neutral and happy, we're going to have 3 strontiums of an aqueous form with a charge that I've yet to denote, and we're going to have 2 phosphates of an aqueous form. And the phosphates are known, common polyatomic ion, be 3 minus. They look like this, by the way. Pretty cool. Double bonded to an oxygen, and then 3 of these oxygens that all have an extra lone pair. That's 3 different minus charges. That's what it looks like. Side note, so there's 2 of them, and they have a 3 minus charge. Over here we have 3 strontiums, must have a 2 plus charge to cancel out the charges on both sides, and that's going to make the KSP of our strontium 2, so that's what we'd call this now, right? Is strontium 2 phosphate. So that's the solid, and it dissolves, and the KSP of it dissolving is the concentration of strontium cations cubed plus the concentration of phosphate anions squared. That is, so we're not calculating numbers here, right? It says KSP expression. What I'm writing out right now are the KSP expressions, the solubility product expressions. They're the theoretical expression of what it is, right? So we have one more of that. Actually, I think you could do that last one. Let's keep moving because it's been 20 minutes. And I actually think I'm going kind of fast. I'm trying to talk fast, and I'm trying to not go off on tangents. I'm arguably doing a tangent right now, but I think it's pertinent. So let's skip that last one. Maybe we'll come back. D on that one. It's the same deal. You get it. You're on it. So it was these two. These are the two that we're supposed to do. My little brackets kind of got moved. Supposed to be these two, this one and this one. And I had to look up what this was and this was. They are less familiar to me, and I'm sure to most people, um, elements. They're both in the lanthanide series, which is that part of the periodic table that's like below the rest of the periodic table. Sorry, let me find where I did this already, because I already looked. There it is. Come back. Where'd you go? Okay. So yeah, they're in the lanthanide series, which is the part of the periodic table that is like you got that going on, and then there's kind of that, kind of back over here. This is very rough. And then there's this box down here. So this lanthanide is the top of that box, the actinides at the bottom. And this one right here, CE, is right there. And it stands for cerium. And it is element number 58. And so this lanthanide series, by the way, is the F block. So just a little background information. Now, why did I why did I even bother looking that up? Because we have to change grams to moles. Why do we have to change grams to moles? It's because we have been asked to calculate the solubility product. That is the same thing as the KSP. The KSP is what we have just been talking about. And the thing about KSP is you have to have molarity. It doesn't equal molarity, so I shouldn't say that, but it requires molarity. A KSP, by definition, is molarities of stuff. So I bring up the fact that this is cerium and it's number 58 on the periodic table because you would have to look it up and figure out its molecular weight so we can go from grams per liter. I know it says milliliters, but that's just like a liter, 0.1 liters. Grams per liters, we have to convert grams to moles to make this molarity. And we have to know what the heck we're talking about in order to get grams to moles, because that's going to require the molar mass. So really quick, let's also just note that IO3 minus is iodate, another common polyatomic ion. So that's just something that you have memorized or that you Google enough until you have it memorized, or however you look stuff up. That's one of the common polyatomic ions. And we can definitely say this, I think, that if you have cerium and it is in a solid salt with count them, four iodates, and we know that iodate, the common polyatomic ion, likes to be at -1 formal charge, then it is very reasonable to think that when these things dissolve in some water, well, I almost made that a parentheses, but I saved it. I should move this. We're going to have four iodate anions, each with a charge of -1, so the cerium must be +4. So by the way, this is cerium 4 iodate, how we would name this. And this means the stoichiometric coefficient here is 1. Stoichiometric coefficient here is 4. Ah, the plot thickens. And the stoichiometric coefficient here, by the way, is 1. Also, now would be the perfect time to bring up a Rice table. So there's our reaction, right? Initially, we have this solid lump of sodium iodate. And we have no sodium, by which I meant cerium iodate. And we have no cerium cations, and we have no aqueous iodate anions. And some amount of this breaks off for us to reach equilibrium. And technically it's a solid lump minus x, but since it's a lump, it's still a lump, and its activity is still 1. So as far as our equilibrium expression is concerned, the solid is still just a solid. It's still a 1. But for every x that we lost from the solid, we definitely gained 1 cerium, 1x worth of cerium, and we gained 4x worth of iodate. So our equilibrium concentrations change initial. Our equilibrium concentration of cerium is going to be x, and our equilibrium concentration of iodate is 4x. And our KSP, based on the stoichiometric coefficients, as we've been discussing, is going to be the concentration of cerium cation to the power of 1 times the concentration of iodate to the power of 4, right? Because 4 is the stoichiometric coefficient. Now, from our Rice table, we have calculated that the concentration, now I'm just using variables, so I'm going to not use the brackets. The concentration of the cerium cation is X. That's what our Rice table said. And the concentration, which will be quadrupled to the power of 4. Do we have a word for that? I'm going to not wonder about it during the live stream. Tesseracted? Maybe it's tesseracted. You got squared and then cubed, and then I don't know if we have a word for the next thing. But to the power of 4, we have determined with our Rice table that the concentration of iodate is going to be 4x, whatever we had lost. Right? So that KSP is going to equal x times 4 to the 4th. Let me not mess this up. I want to say it's 256. Yeah. 256x to the 4th is what 4x to the 4th is. And x times 256x to the 4th is 256x to the 5th. So mathematically, the KSP of solid cerium iodate, IO3 to 4, the KSP of that mathematically is equal to 256x 5 squared. There we go. And we are told, okay, so that's where we would have to stop if we don't have more information. We figured out that based on the stoichiometry, in theory, however much of our starting salt dissolves, the KSP will be 256 times that much if you first put that much to the power of 5, which I definitely don't know the name for that. But we are given a little bit more information, which is that much of it dissolves. For every 100 milliliters of liquid that you have, 1.5 times 10 to the minus 2 grams of this solid does dissolve. So the thing is, we could use that for X. That is what X is. That's the molar solubility. Sorry, it's not the molar solubility. That's the solubility by mass, I guess. We just need to convert it to molar solubility in order to use that and get a standardized K. So, sorry, I should have 1.5 e minus 2. So we have 1.5 times 10 to the minus 2 grams of our solid. I should actually not phrase it like that. That's how much dissolves. Grams dissolved. Dissolved. Let's just go the whole 9 yards and name it by name. That many grams of dissolved cerium iodate, cerium 4 iodate per 100 milliliters, which is 0.1 liters, right? And then if you add it all up, you look at your periodic table and get all the masses and add it all up, or just Google it or get it on the internet some other way. I think once you've proven to yourself that you can figure out molar masses, it's totally awesome to just look them up. It turns out that the molar mass of cerium 4 iodate is 839.7 grams per mole. And so the grams cancel, and you do that math, and you get that there are 1.786 times 10 to the minus 4 moles per liter, right? Because those are the units that we have left over, moles per liter. Cancel that grams, and I clarified that I meant grams of this stuff. In this case, it was not that necessary because we don't have other stuff that we're really talking about. But sometimes it's very handy to be clear that you're talking about grams of this and moles of that, even if they're the same thing. Better to be too clear for your own sake and if you're trying to communicate. So back to the matter at hand, that is going to equal X. That now is the molar solubility. It basically means that if you had less than this many moles per liter, you could dissolve the cerium 4 iodate. But if you try to dissolve more moles than that, the excess will precipitate out. So that's how much of it can dissolve as a concentration. If you had extra liters, if you had 100 liters, 1,000 liters, a million liters, you could dissolve quite a bit of the stuff. If you don't have a lot of liters, if you only have a milliliter, or in this case, 100 milliliters, which is not that much, by the way. 100 milliliters on this seltzer can here is, this is, it says right on it, 12-ounce can is 355 milliliters. So 100 milliliters is like a little bit less than a third. It's like 2 fingers worth of can. So it's not a lot. 100 milliliters is pretty small. Anyway, I said no tangents. I think that was directly pertinent, but let's actually get more mathematical. So now we found the molar solubility, but we just have to tie it all together with our KSP, which we calculated algebraically, going to equal that, and we just determined that that's X. So the KSP of this cerium 4 iodate equals that, and you do this to the fifth first, right? You know the order of operations. So important. And it's so important to not trust your calculator to know the order of operations. Parentheses are free. Use them. If you do that math and you do it correctly, or I should also add, if I did it correctly when I did this a couple hours ago, and I was preparing for this, then you should get 4 point, and I'm just rounding for sig figs here. You get a lot more digits, but it basically is that. By the way, 10 to the minus 17, tiny. That basically means that cerium 4 iodate is not good at dissolving. It prefers to remain a solid, thank you very much. Okay, let's do the next one. And the more of these we do, hopefully the more I can just sort of assume you follow what I'm talking about. So first off, this GD is called gadolinium. Let me just take a picture of that. Okay, so gadolinium, it's in that same series as the lanthanide, number 64. And by the way, I just already looked it up. The molar mass of this, since you know we're going to need it based on the question and the information, the molar mass of our compound here, this solid salt, is 602.7 grams per mole. And when our gadolinium two sulfate, or there's two of them, and there's some sulfates, that's going to dissociate, and we're going to get two gadoliniums. D. We're going to get two gadoliniums and some, by which I mean three, sulfates. And sulfate, again, common polyatomic ion. Sulfide happens to be a S2 minus, and so does sulfate. By the way, common polyatomic ion. Well, sulfide is not polyatomic. Sulfates is, though. And we know it's 2 minus. If there's three of them and they're 2 minus, that's a -6. We have two of these. It must be -3 to balance the charges out. So the name of this is going to be gadolinium, gadolinium, gadolinium. That'd be a plus. Gadolinium 3 sulfate is the name of this, by the way. And the KSP, let's just call this G3S for the moment. The KSP of G3S is going to equal the products, which are going to be the concentration of our gadolinium cation squared times the concentration of our sulfate cubed. And if you think about the rise table, right, I think you can just do this in your head. I'm going to assume you can. Hope you can, so that we can answer as many questions as possible. The concentration for every one of these, for every x of those that we lose, we're going to gain 2x of these, and we're going to gain 3x of these. And this is a lump, so whatever on that. But yay for gaining ions. So the concentration will be 2x of whatever the molar solubility of our starting salt is, and the concentration here will be 3x cubed is going to equal our KSP. So that's our equilibrium concentrations of those things. To push the math here forward a little bit, this turns into that times that. 4 times 27 is 108, and x squared times x cubed is x to the 5th, and now we just need sulfur x, and we're going to do it just like that last problem, where we have x is going to be the molar solubility, and we're given the by mass solubility. So that was 3.9. This is a lot more, by the way. The last one, right, that we did was 1.5 times 10 to the -2. And this is like actually a full number. So this is going to be much more. Per 0.100 liters times. And of course, you write out the units every time so that you remember to put the grams on the bottom here so that you cancel them out and you convert this correctly per mole, and you do that math. And when you do, you get that the solubility, the molar solubility, 6.0 times 0. I have too many points there. Apologies. 6.6. Let's just call it that. It's not a sig figs kind of thing. Probably have one more sig fig, but we're just gonna leave it like that for now. And that's X. That's our molar solubility. So that means our KSP for this one is going to be 108 times that number I just got, which I'm going to actually write with the extra sig fig now, since I'm writing it again. Where found it, lost it. There we go. 6. Oh, the extra sig fig was not that cool, but there you have it. The 5th. So remember, of course, this to the 5th first, and then the 108. And you do that, and you get. So this this KSP times 10 to the -4. I mean, it's not great at dissolving, but it's way better then this one. Times 10 to the minus 17 is tiny. Times 10 to the minus 4 is small, but bigger than the last one. So this stuff is better at dissolving than the last stuff. So, okay, let's charge on. We have 20 minutes left, and I'm definitely going at the fastest pace. This is my fourth time doing a live stream, getting the hang of it more and more. So, calculate the molar solubility. That was the thing I just kept talking about. And chances are, well, no, it says from its solubility product. So we're looking at lead bromide, silver iodide. So let's just look it up now. It tells us we're going to get it from the solubility product, which is basically going to be this. We had lead bromide right there. And just because I like to challenge myself to remember things, but just so I don't mess anything up, I'm just going to do this one like that. So there is the KSP of lead bromide. And the other thing was silver iodide. And by the way, we can sort of assume that as long as this question, oh, I just got fooled because silver, AG starts with silver down here. Okay. Uh, we we can sort of assume that this question isn't like messing with us and trying to just trick us and lead us astray, and that these things do have KSPs at all. But that said, it wouldn't be a bad idea once again to look at table 4.1 over here and just confirm. So we've got bromide. Oh, let's see. Oh, bromides are soluble. This was lead bromide. It is soluble, exception if it's with lead. Okay, so that's why that's not soluble. BR, or sorry, PbBr2. Lead 2 bromide is not soluble because of that exception. And our other one, the silver iodide, same deal, right? Iodide is soluble, exception if it's with silver, right? So by that token, silver bromide also would not be soluble. So I just thought it was fun to confirm why these are not soluble. Back to the actual question here. So uh, let's just do these one at a time. I'm going to try to do this as quickly as possible and hopefully be only minimally sloppy. So reversible reaction, we get lead 2 because bromide is invariably going to be -1, and we have 2 of them, both aqueous, and this means that our KSP is going to equal the concentrations of the 2, and that the concentration of this one is going to be squared. And we know that for every 1x of that, we're going to get 1x of that and 2x of that. So the KSP is really going to equal x. And by the way, we are solving for x here, right? That's the whole point. So the concentration of bromine is going to be 2x. And so that's going to be x times 4x squared. And that is going to equal 4x the fifth. And fifth, seeing if you're paying attention, sorry, x times x squared is to the third. And that is what the KSP for this compound is. So if 4.6 times 10 to the minus 6 equals 4x cubed, then it must be that x cubed equals 4.6 times 10 to the minus 6 divided by 4, and therefore it must be that x equals the cube root of 4.6 times 10 to the minus 6 over 4, which, by the way, that is the same thing. Your calculator might work better if you do it like this. To the 1/3. That's the same thing as a cube root. You probably already know that. But if you don't, or you needed the reminder, that is how I frequently would do this in my calculator. I would have this divided by that, and I would say the answer of that to the 1/3. I might get one of those on-screen calculators going one of these days, but for now I don't have that. We solved for x here. We solved that for x, and I did this a few hours ago. And it was 1.05 times 10 to the minus 2. I would do it again, but in the interest of time, I'm just going to trust I did it right the first time. I'm going to hope I did it right the first time. And that is what we were looking for. The molar solubility of that compound led to bromide. Now, that means that for every liter of water you have, basically 1 times 10 to the minus 2 moles of lead 2 bromide will dissolve into it. All right, silver chloride. Same deal, except for you can already tell, right? Silver chloride, it's going to be silver chloride, and the KSP is just going to be X times X, right? I mean, it's going to be that times that. So messy. I'm going so fast. But for every X of this, X, X plus, plus, right? So that means the KSP simply is going to be X squared. No stoichiometry to worry about, basically, in this case. And so the KSP table said 1.5 times 10 to the minus 16 equals x squared. So x equals the square root of that, which again, calculators tend to have the square root button, but if you wanted to, do it like that. And so x on that one for silver iodide, oops, I meant to say iodide here, iodide, my bad. Sorry, iodine, iodide, not chloride. Is 1.22. And now let's just compare them for fun. Molar is the molar solubility of silver iodide. So silver iodide, you can only dissolve that's like a 1.2 times 10 to the minus eighth is like basically a billionth. That's like nanomole. That's like a billionth of a mole per liter. Whereas with lead bromide, that's like a hundredth of a mole. So way more. So neither one is excellently soluble, but lead bromide is way soluble compared to silver chloride. So, all right, pretty cool. Let's keep rolling. Making good time. 13 minutes left. Like I said, I might go a little long. I might not. Oh, here we go. I see. Okay. So this one is interesting. Once again, I apparently left my notes in from before. This confused the heck out of me for a sec because I was like, what? No, those are not I's, those are L's. Can somebody please go back to the ancient Latin alphabet creator people, who I guess were the Romans or the Latins or whatever, and ask them to not make capital I and lowercase L the same thing? It's horrible. It's horrible. Whose idea was that? So bad. So I'm gonna try to do my L's like that, even though it's unnecessarily froofy, to just be super clear that in this case those are not I's, they're not ones, they're L's, and that is something called thallium, thallium chloride. We know, by the way, that chlorine loves to be a chloride minus one. Thallium must just be thallium plus one. So that means the KSP of this, by the way, is just going to be x squared, right? Whatever x of that we lose, I'm not going to over explain that now because we've seen this again and again. KSP is going to be that. So did I have to look up the KSP of that? I think I probably did. Yeah, looks like I did. By the way, this is in that table. We could go look it up, but I already did, so I'm just going to write it down. This is from Appendix K. No way to know this without doing the experiments or looking up yourself. Uh, or sorry, Appendix J, my bad. Solubility stuff. Solubility products. Appendix J. That appendix says that the KSP is 1.7 times 10 to the minus 4. And that means that if we're ignoring the hydrogen chloride for a sec, the hydrochloric acid, that means that 1.7 times 10 to the minus 4, the KSP, equals x squared. So x, the molar solubility of tellurium chloride, equals the square root of 1.7 times 10 to the minus 4, which is 1.3 times 10 to the minus 2. However, that KSP expression, of course, this is sort of this very similar to the concept of what we looked at the very beginning here. KSP is going to equal that cation times that anion. And KSP is this fixed quantity. It's just a property of tellurium chloride that the KSP is 1.7 times 10 to the minus 4. So if the chlorine goes up, the tellurium is going to have to go down, right? So how does the chlorine go up? Well, we have 1.25 molar HCl. So that's a strong acid that fully dissociates into H plus and Cl minus. When we're talking about acids and bases, we tend to be interested in this. But now we're actually interested in the common ion, right? HCl provides an ion that tellurium chloride also provides. Common ion. It's an ion that they have in common. The common ion. And that means that this fairly strong, I mean like quite strong, hydrochloric acid at 1.25 molar is leading to 1.25 moles of chloride here. So on its best day, this is molar right here. And when I said moles, I meant molar. However, if we pretend we're looking at like 1 liter, then we could say moles. But I'm going to say molar, so my bad. So if we have 1.25 molar chloride coming from our hydrochloric acid, and at best, the X that we solved for before when we didn't have hydrochloric acid was 1.3 times 10 to the minus 2. So 1.25 versus 1.3 times 10 to the minus 2. So this is way more, right? That's way more chloride ions than this. Now, I calculated it both ways, but this question asks us to show that the changes can be neglected. The initial concentration. Basically what it's saying is that whatever chloride is coming from tellurium chloride is going to be dwarfed by the chloride that comes from hydrogen chloride. And we can basically ignore it. To test this, I did it both ways. So if we neglected it, let's actually do the not neglected one first. So if we don't neglect it, then the KSP is going to equal the concentration of tellurium won't change. So that's still going to be X. But the concentration of chloride is now that. And you do some math, right? Because we know that this is 1.7 times 10 to the minus 4. And one thing leads to the other, and you've multiplied this, divided that, whatever, subtracted this, and you get a quadratic equation. That if we weren't nearing the end of the session, I would have done all that math right now, but I'm just going to trust that I did it correctly a couple hours ago. And if you put this into a quadratic solver, you get that x equals 1.13 times 10 to the minus 4. That's a solubility product, which, by the way, that is quite a bit lower than that, which is irrelevant. That's the wrong thing. My bad. That's quite a bit lower than, what am I looking for? This. They're very similar. No, they're not. Sorry. That's what I meant. This is quite a bit lower. So doing this in the hydrochloric acid, when there is hydrochloric acid, the solubility went down by like 100-fold. We have to the -2 up here, to the -4 here. So that means that the tellurium chloride would be more of a solid. It would precipitate out. But now let's see if we had neglected. So this is not neglecting is what we just did. The concentration of chloride there. We neglecting, if we don't neglect it, we get that. But if we do neglect, then we're just going to get this. And that means that x is, since our KSP is that, x is just going to equal our KSP divided by 1.25. And when you do that math, you get, which is literally exactly the same. Maybe there are going to be a few sig figs off, not sig figs, maybe there'll be a few decimal places off when you go down a couple more decimal places, but for all practical intents and purposes, they're the same. So that's why we can, if we have essentially an overwhelming or swamping concentration, swamping, I don't know if that's actually officially swamping, but it's swamping-esque concentration of the common ion, then you can neglect or ignore the contribution to that common ion from the thing you're dissolving. Okay, let's look at this one. And I think we're actually nearing the end of solubility. It always takes me like 2 or 2.5 hours to go through these before I live stream. So it's pretty ambitious to think that I could ever get it done. So without too much explanation, let's just bust this out. I have looked up the KSP of this in Appendix H, Appendix J, I mean, sorry. And it is 1.4 times 10 to the -8. And I'm going to hope you trust that we can ignore or neglect that number like last time. And this, of course, leads to 2 iodides, right? Not very soluble if you think about the table that we just looked at, but that means that our KSP expression, if you think about it, is going to be, if we lose x here, x, 2x, we gain. Our KSP expression is going to be x times 2x squared, which is going to work out to 4x cubed, like we saw earlier, and 1.4 times 10 to the -8. Now, this is if we didn't have the other stuff, right? So if we solve for x here without the other stuff, which is not really asking us to do, but I just sort of instinctively do it, then we get 1.52 times 10 to the -3. However, if it's in the presence of that common ion generating calcium iodide, which that's going to lead to if it's in the presence of that, then the KSP of our lead iodide, with all these extra iodides around, is going to basically equal the concentration that we're given here. That's going to fully dissociate. We're going to get a ton of those, except for when one of those dissociates, we get 2 of those. So we're actually going to be that molarity times 2, which equals that. So it's going to be whatever the concentration of lead is times twice that, and that's going to be squared also, right? Our KSP expression is squared over there. So even though we could have also, what we're neglecting is to add a 2x from there into this. We're neglecting it because we sort of already demonstrated that we can do that when we have a much larger concentration from something else. And what we're going to get here that that equals, so, right, there goes what's happening. It's going to equal x. And you do that math, which I hope you can do. And x is going to equal 2.78 times 10 to the minus 6 molar solubility of our lead iodide. And again, without common ion, it was times 10 to the minus third. With the common ion, it's times 10 to the minus 6. So huge decrease in solubility. We see once again. All right, so it's 9 o'clock. It's been an hour. Well, there's exactly one solubility question left, and there are 3 entropy questions. And the thing is, I'm super tired. I've been doing a lot of my own homework and stuff. We just did a lot. It was a lot. And I already did this once a day. So I think I'm going to save these last questions for a future video. If you've watched any of the other videos, I apologize that my cat only showed up in the first one. I don't know where. Oh, he's right here. So, hey, buddy. Hey, buddy. Say hi. So there's my cat, Diego. He actually loves being on camera, basically. But I did this standing today, so that's harsh. I guess that's why he wasn't really in it. But okay, so first off, sorry I didn't have more cat. Here's what I really importantly wanted to say is that I do intend to post some supplementary videos where I either go more in depth on some of these questions or I fill in some gaps on things I didn't finish, like today. So that's why I bring up past videos. I've said I'm going to do that. I'm still planning to do that. But for now, I'm going to call it a day and post those final questions some other time. So have a great weekend. Study hard. Let the units be your guide. And see you next time.